Well, it is a pleasure to introduce the last morning of this conference with Leonardo Cavenaghi from CAMPINAS. And he will be speaking about a symmetric approach to general relativity applications to intelligence. Leonardo.
Thank you very much for attending here. If there's any problem about reading the versions, let me know. I'll do my best to make it more clear. And it's a great pleasure to speak here. I'll try to give you some ideas of things that I've been doing with Professor Leonardo, that is also from CAMPINAS. This is a joint work. And indeed, it is just the first work of a series of work that we intend to do about providing a different approach to general relativity using symmetries, especially something that's called cross diagrams that was introduced in the beginning by Carlos and Rigas that work in Brazil. And the main motivation to our talk is about how different differentiable structures can determine or possibly obstruct the geometry and physics. Because I once recalled that, well, at least the foundation of quantum field theories, it begins with a principal bundle here. I'll always denote the fibers of the principal bundle by these dots. I hope you can see this. Yeah, and this is straight to marker. Yeah, for sure. It's best, right?
Yes.
Okay. No problem. So we have like the main setting to quantum field theory consists of a principal bundle with structure group G and some base manifold B. And we usually take, for instance, like an associated vector bundle. Let's put it like E equals. We take generally like the conjunct action here to produce another bundle. Here there's a vector bundle associated to a principal bundle, and then we take some special connector here on this vector bundle. This is usually the beginning framework to do quantum field theory. And this is mostly because of this holy history about Yang and Induce that it began long time ago, when they usually take G to be SU2 and the base manifold to be S4. And the main idea is that because at the time there was a hidden symmetry between these low energy interactions between subatomic particles. So they modeled the symmetries to some particles in low energy levels by this SU2 group. But when we pose like this setup with the quantum field theory, naturally we are assuming that we have a principal bundle. So we have a D group that is supposed to have a smooth structure, but we never wonder what is this smooth structure that we are taking, because in the 50s, more precisely here, Mueller discovered what are called exotic spheres. So he proved that there exists a manifold of dimension 7 that is homeomorphic to the standard sphere, but is not diffeomorphic to it. And the way that he constructed this was quite topological, and when he was doing this procedure, and indeed this M7 is the total space of a sphere bundle, which fiber is SU2, and the base is S4. So this is a natural connection with the Induce theory here. And so this M7 are just the total space of bundles with fibers and waves and spheres, and he thought he had a counter example to the Minkowski conjecture. That was something that was surprising. But then he realized that when computing some differential topology invariants, these manifolds necessarily had to be not diffeomorph to the subject sphere, but he was able to produce a function, not function, with domain here in N7 that happens to be exactly two critical points. So the point of view of real sphere theory, this N7 should be homeomorphic to this subject sphere. So something that I usually wonder is about when we look to the verses of Riemannian geometry and we start to working with some metrics and the curvature aspects, the best results that we know about relating curvature properties, so geometric properties and topological aspects, are just in the setting of one set topology, like Bonnet-Myers theory, or Sinji's theory, or Hadamard theory. Why cannot we say something about the economic structure? Since when we start to begin doing geometry, we are already assuming the existence of some atlas, and then the metrics are compatible with that atlas. So this is more or less a motivation to our aspect. And indeed, in the 80s, Witten, he was wondering about these exotic structures and how this could be employed in physics. Later, he was much more explored. And I want to bring you to approach aimed to ask the question that we are beginning to approach the following question, that is to what extent differentiable structures determine or construct physics. But why do we care about physics? And the short long story is that since we know a lot of different exotic structures, for instance, nowadays we know that there are 7-dimensional manifolds with 28 pairwise non-diffeomorphic structures on spheres, topological spheres. Topological spheres. So to 7-dimensional topological spheres, and by topological spheres, I mean that this manifold is homeomorphic to a 7-dimensional sphere from the point of view of topological manifolds. Then we can find 28 pairwise non-diffeomorphic atlas to make this move manifolds. So these manifolds, though are homeomorphic, they are not diffeomorphic as this move manifolds. But then we also have, like in the 8-dimensional case, there's 2 non-diffeomorphic structures. So we have a classical smooth structure and the exotic structure. So we have like 2. And to anything, we have 20 more. I don't exactly recall the number. But one thing that is interesting is about, we don't know much about the geometry of these manifolds. So for instance, until these days, we do not know if any of these exotic manifolds are metrics of positive sectional curvature. We don't know this. But even worse, to the some 10-dimensional exotic spheres, I mean, we have a topological sphere with a non-standard atlas. There are some manifolds on the 10th dimension that do not admit metrics of positive scalar curvature. But this is something that we more or less know why this holds. The only manifolds, 10-dimensional exotic manifolds that admit metrics of positive scalar curvature are the ones who can be made like the boundary of some spin manifold. This is a result of teachings, like teaching. So the geometry here is not well understood in the setting of this movement. We could then think a way of trying to understand how can we distinguish geometry aspects if lies to us theorems relating differential topology and geometry. Just because I said this one and I theorem are just by the concept topology aspect. And the way of doing this is perhaps to look to physical aspects in this manner. Perhaps we could try to understand the physics there. Then there is a way that we can try to find structures to the admissibility of some special topics. And that's how the history began to us. Something that I want to say related to this is that a lot of work has been done from the physical side about the exotic Euclidean spaces. For Euclidean space, only R4 has non-diffeomorph smooth structures as manifold. Indeed, it has uncountably many different smooth structures. But here, there is always a amount of smooth structures that are comfortable and finite for each fixed topological manifold. And in today's talk, I'm going to present to you some specific constructions on classical and exotic manifolds that can be interchanged in the physical meaning. So we are going to use semi-Riemannian metrics, more particularly Lorentz metrics on classical and exotic manifolds that have the same topological global aspect and even the same geometrical aspect. So as spacetimes, they are indistinct. We cannot distinguish no physical aspects. And I wonder that this is mostly because of the way that we realize the time. And perhaps there is something even more deep even here that I want to present to you. But, well, we could ask, for instance, why are these exotic spheres so special somehow? And one thing from the physical point of view that I can explain to you is that no exotic sphere can be realized as a homogeneous space for a given group. So exotic spheres are never homogeneous space. So what is a homogeneous space if one thinks by the physical philosophy? Then imagine a homogeneous space is nothing but one orbit, one large orbit. So the idea is that when we look far enough to the horizon, then the space should be we do not distinguish to where we are looking. Since looking very far from here, the space should look exactly the same, no matter the direction that we are pointing out. So this is what called the isotropicity hypothesis in the physical point of view. The universe looks like the same, no matter the direction that we look. And so exotic spheres are never homogeneous spaces. So they could not be good candidates somehow to the physical models. But the point and the intriguing aspect is that, well, they do not distinguish here global geometric aspects by the construction that we talked about. So it seems that this isotropicity hypothesis should not be a big deal somehow. But how can we do these constructions? And I'm going to present it explicitly to you. And just as I said, this began mostly in Brazil with Carlos and Higas, but earlier it began with the idea of two guys named Bruno and May. And this is an outstanding construction that I'm going to present to you because it was the first realization of some exotic sphere with a method of non-negative sectional curvature. And the construction is quite simple. You take SP2 to be the Lie group. We're going to put it here. So each column here shall belongs to S7. So each entry of our matrix is nothing but a covariant. So we have A, B, C, D, belonging to the quaternions, and the columns are orthogonal. And since each column belongs to a 7, we have that the square norm of A plus the square norm of B equals to 1. Same for the square norm of C, square norm of D. And then we can take here G to be SU2. Okay, that you can just think as the unity quaternions. And we can introduce two different actions of SU2 on SP2. The first one I'm going to introduce here, and then there's a reason why I'm writing it on the right. And this action is nothing but, just let me not fix, just nothing. I don't want to write it wrongly because there are some cautions we have to make here. So we are going to just add by multiplying the second column. And you can check that this defines a free SU2 action on SP2. This action is free, but more interesting, we can define a quotient factor so we just put the projection of SP2 to S7, and recall that each column belongs to S7 itself, so we can put this here and send it to AB that belongs to S7. And so this projection maps becomes a quotient map for this principal bundle with SU2 action. So we have a principal bundle here with fiber SU2. But then we can introduce another action, a more strange action on this SP2. So we take here A, B, C, D, and then we just define this action to be E, A, Q bar, Q, B, Q bar, T, C, D. So this is a different action here. And we can introduce a quotient map that is given by, well, we take this matrix here and we send it to 2 C bar D C square minus D square. And this is a quotient map to another principal bundle. So this action here, they also defines a free action on SP2, an SU2 free action on SP2, such that for this quotient map, the ordered space SP2 under this SU2 action under pi prime is nothing but a 7-dimensional exotic sphere. This can be shown. So the action here on SP2 imposes isometric structure on S7 as quotient. So the thing is that we could produce a diagram that we name like a cross or a side diagram in this manner. We have SP2, and then we have what we call this bullet action, that is the principal action here. So I'm going to call this bullet action, and this one I'm going to call it star action. And then we have with pi being the projection, the standard sphere, but then we have star action, and we obtain a 7-dimensional sphere. And Why use manifold? This is what is here in the method of non-negative sectional curvatures, just because we can, since SP2 is a compact figure, we can take a bi-invariant geometry there, so it has non-negative sectional curvature, and by introducing a Riemannian submersion method on sigma 7, since Riemannian submersions do not decrease sectional curvature, the natural equation naturally has non-negative sectional curvature. So this is how Roman and Nader construct their first example of manifold non-negative sectional curvature. And the main idea here is that this example shows a basic model to analyze physics on exotic manifolds. But this construction can be made much more general. You can produce almost every exotic manifold by diagram like this. And how can we do this? And why would we be interested about producing metrics of semi-Riemannian metrics? Semi-Riemannian metrics on this spaces by this means is just because this particular diagram is just a particular case of a more general construction that can be made by the means of a Morita equivalence between some manifolds. This is some hidden aspect here. So in general, how should we proceed? We are going to take P as the total space of some principal bundle, and we're going to have a group G acting by the means of a principal action bullet that builds as quotient a manifold, but we also going to build, like in a systematic way, another action that we're going to call and denote it by star, by the same group G, and these two actions are commute. The two actions commute on P and use as quotient a manifold M prime that is homeomorphic but not diffeomorphic to the standard sphere. And this is going to be a Morita equivalence. But why is that? Because, well, since these two actions commute on the total space, then this star action descends to D action, G action here on M, and also bullets descends to a G action here on M prime. In general, these actions on the quotients shall not be free. But when we take the orbit space, according to these actions, we can provide Riemannian metrics on the regular strata, but even metric space metrics in a manner that these two here are isometric as metric spaces. But mostly interesting, each orbit of the bullet action on M prime and the star action on M are diffeomorphic. And each G-invariant submanifolds can be made, we can build G-invariant tubular neighborhoods on the orbits of these manifolds that are G equivalent diffeomorphic to each other. So from this point of view, these two manifolds on the quotient look like locally indistinguishable. So what is hidden there? Why could we produce differentiable structures if locally these manifolds look very similar, even they have two each orbits diffeomorphic to each other? What's going on? The problem is with when you do the grooving aspect of this kind of thing. And here I'm going to present you a very basic example of this cross diagram that's going to help us to build semi-Riemannian metrics on classical and exotic manifolds. But now I can tell you in advance how can we build semi-Riemannian metrics that enjoy the same physical properties. And then it's quite simple. It's just because if we are able to produce a semi-Riemannian metric here, then we can, by the means of a Lorentz connection, to make a semi-Riemannian metric here on P in a such manner that this is a semi-Riemannian submersion, and then we just induce on the quotient another semi-Riemannian metric in a manner that these two shall have the same horizontal geometry, or so the Riemannian geometry. So this is the idea. And more or less, is to see like about this field duality stuff where you can transport geometry. This is not about the transportation of some geometric aspects. Like if this manifold has positive ridge curvature, we can ensure this one to have positive ridge curvature as well. But why can we do not do this with sectional curvatures? That I don't know. But it simply doesn't work. But to weaker geometries and even to produce semi-Riemannian matrices, special Lorentz matrices, we can do this procedure. And how are we going to build semi-Riemannian matrices? Well, we need a time-like direction to be the time orientation of our manifold. Well, we're just taking G to be S1. And this S1 shall give us the group of symmetries in a manner that the actual vectors given by S1 are nothing but the pointwise values of the time-like global vector of the manifold. This signal that. But how can we take a look to? You may wonder, how are these actions described locally? And there is a very simple description of these actions locally by looking to a global example. So let us begin with this toy model, but it's not toy at all because this is nothing but what is called Cheeger deformations. Cheeger deformations were introduced in the 70s by Jeff Cheeger, aiming to produce matrices with no negative sectional curvature, mostly on some homogeneous space and homogeneous monomanifolds. And the idea is the following: we have a manifold here, a Riemannian manifold with a group action that need not to be free, only if it works to us, but the action need not to be free. And what shall we do? We are going to take M times V, and we are going to introduce here an action, bullet, and an action star that yields us quotient here, in this case, nothing but M and also M, but with different metrics if we perform some choice, good choice for the projections. For instance, for this one here, we can just take the first factor projection. And here we can take this phi prime. But what is the bullet action? We can take G, and this acts on X, G prime, just by right multiplication. So it acts only on the unit factor. And the projection on the first factor does not. But then we can take this star action and make the associated bundle construction. So we take Gx and then G prime. And the projection is just the orbit projection for associated with bundles. And then these two promotes the same manifold when you take the projections, but with different angular horizontal distributions. And you may wonder, what is a horizontal distribution in this sense? You could make it to be any choice of complementary space to the kernel of the projections. But we can do this in for special way. For instance, to this n times d, we can consider the metric G times 1 over T Q, where G is the Riemannian metric, T is a real number, and Q is any bi-invariant metric on the Lie group. So we consider this metric on the total space, and when we take this pi1 projection, the metric here is nothing but G, but the metric on the quotient, it depends on the parameter T by this star. This is what we call a Cheeger deformation. This GT metric is what's called a Cheeger deformation of the metric. And one thing that we should note from here is that T usually is taken to be positive. So we can reduce everything and that indeed on the quotient. But now I'm playing to you that we're going to take P to be negative to produce semi-invariant matrix. Because if G starts to be a bi-invariant matrix, if you take Q to be also bi-invariant because it's a bi-invariant matrix, so GS itself, then we can produce invariant matrix on the quotient by the D group, and indeed semi-invariant matrix. And this is the main idea on the whole thing. And this is how this procedure works. But one interesting aspect here is that our construction to the general case of each pair of manifold and exotic manifold locally on trivializing open sets for these bundles, these cross-diagonal bundles, the actions look like these ones here. So locally, the bullet action on a diagram like this behaves like action on the second factor, and the star action behaves like associated bundle action. And the general procedure to do this construction shall be made in some moments, but let us see how we obtain the classical Minkowski space and its symmetries from a construction like this. So, because the construction would works as no good purpose if we wouldn't be able to recover some classical stuff. So, what's the idea? I'm going to take here the quaternion space. Let's put it here. One impulse. Space. Via Cheeger deformations. We can take our manifold and to be the quaternions. That's nothing but R4. So we have a point here that we are going to denote like 0, 1, 2, 3. This one here belongs to R4 that we're going to identify with 0 plus x1 where of course EJ equals 0 and this unit patterns. So we have this, and what we are going to do is to make an R action. The D group R itself is going to act on this Minkowski space, so we take G to be R, and then we have this R action on the hyperbolic space. We take this P, and we define an action here on Q, just by translating the first word. We have this P plus this personal translation of the first word. Now, what do we do? We are going to make the Cheeger approach to induce a family of time parameters measured on the hyperbolic, quaternion space, and to recover the Minkowski magic on it. And how can we do this? Well, we took M to be the quaternion space and G to be the reals. So we're going to take this product here and consider the twisted action. Once we consider the twisted action, we are taking some product metric on the product space, and then use that on mathematics. And then we compute the vertical space that's only related to the action, and the horizontal space that is complementary. And computing the norms of horizontal vectors, we shall determine the manifold quotient. And this is going to be the Minkowski method. So we do this. We take H times R, and then we add here with R by this timing. So we have a point Q, and we have D prime, and then we add it with D, obtaining T. So we get this action here. And on this space, we consider the metric, the Cavenaghi metric here, minus, we're going to take r squared d theta squared. So we have a metric here, minus x squared. So we have a metric here on the quaternion part, and we take the standard metric on the reals, but we deform it by a negative of 1 over a positive number. And we have this metric here on the product that happens to be invariant by the R action, naturally, and we can compute the vertical space for this star action on the total space. And this is nothing but, well, let's compute the action vectors for this action to its point. And then we take the horizontal space to be the complementary space according to this method that we just introduced. So I'm going to write this for 15 to you. So what I mean is that we can take the vertical space that I report to you that is the tangent space to Leonardo, right? So the vertical space at Q, P prime, as you can easily see, is the span space by. We just take the derivatives, so it's just 1 plus this. 1. And then we have to take the horizontal space at this point. That is the G-tube complementary space to this vertical space. Okay, this is just standard definition. We are choosing the horizontal space to be the complementary according to the vertical space. That's the space that collects action vectors. So the horizontal space here in this space has this expression here, just the expand R. The vectors x written as x d prime belonging to the coterminus times t prime such that x then be written as r minus 2 d prime plus x1 plus x2 j plus x3 k d prime. So we have this is the horizontal space, and when we can compute the norm of vectors on the horizontal space, we can see that, well, the norm of this vector here, according to the G-tube metric, is just given by minus d prime square r to the power minus 4 r2 minus 1 plus the imaginary part of this quaternion vector. Now we conveniently choose c squared to be r minus 4 minus 1, and then this is just minus t prime square c2 plus the imaginary part of x squared. This is just the standard Minkowski rank in this way. So we could do this like with many other cases, but this is how we can derive the standard Minkowski space from the Cheeger procedure. Yeah, okay.
This, but R is this in the origin?
Yeah, sorry. No, sorry. Yeah, that's my fault. R is just the time parameter here that we are taking to the metric. It's just a positive number. We are taking a positive number and we are taking this metric here. R, this is R.
Okay.
R is just a positive number.
We call T before this.
Yeah, I was calling it T, but since I'm talking to the reals.
But when we call C squared, it might be negative somehow.
No, it's not. Just because I'm taking always this to be I squared is necessarily less than 1. I'm choosing, so I choose this in a manner that this is positive. Because I have the freedom to choose R. I can choose any R that I want. And this is an important aspect. Because figure deformations may or may not lead to similar Riemannian methods. It depends on the parameter that it takes. For instance, if the parameter T, but now is 1 over R squared, is greater than the norm of the operator, the orbital map, then it will not. So I have a choice.
Yeah.
Indeed, I have a family of possible Minkowski metrics. Yeah, so yes, thank you for pointing this out. So this is some real number that I'm choosing here. So I choose it, choosing it so that R squared as well is breaking the 0. This is an important aspect. And this is a possible construction. And since you just pointed it out, I'm just going to change a bit what my intention to present, and I'm going to show you how the original metric quantities of a G metric is related to a deformant metric. Okay, so now before proceeding to examples, let me just begin with a manifold. And we make a Cheeger deformation, but now I'm going to use the R parameter just to be constant. I'm going to take like this Cheeger here, R4. And well, here, since we do have like actions on the manifold, I'm going to lose a bit the notation, and to each point, I'm going to write is as vertical space plus its G complementary space Hx. But since the action needs not to be free, it's important to remark that may have fixed points or may have points where the isotropy is higher. So this vertical space, when you collect it parameterized by x, it does not define the bundle, it defines a shift. So because the dimensions of the vertical space can go lower than, but there is always an open and dense convex subset that we call the regular stratum, where two points have conjugate isotropies. And so by conventioning this, I'm always going to say that the vertical space is the tangent space to an orbit, and the horizontal space is nothing but it's complementary. But here, the tangent space, it is diffeomorphic to, and I'm going to use this notation to the algebras, where the B algebra of G can be written as M plus the isotropy. I'm sorry, at some point X. So this is the X. So for fixed points, we do not have this space here that is isomorphic to the tangent space of the orbit, because the isotropy is everything. But then, if we fix Q to be a bi-invariant metric, on G, then G relates to Q on the vertical part by some tensor here. Oops, well, O. This is O. This is the orbit tensor. The metric of the vertical part, that's the tangent space of the orbit, relates to the manifold on the Lie respect by a positively symmetric tensor that we denote by O. And for a Cheeger deformation, we have G. It can be T. It can be composed as some horizontal part, and the method remains unchanged, plus a GT on the vertical part. And GT on the vertical part, it relates with you by some PT. Oh, sorry, it's OT. And OT equals to O1 plus, I was using R, and then I'm just going to use, let's use it E from the beginning, because I'm going to take something different here. O plus. So the point is that if we take T to be negative, if 1 plus TO is lesser than 0 as operator, then the matrix is degenerated, it's Riemannian. So this is why we have this choice about taking R to be lesser than, to be greater than 1. So we take here T equals to minus R squared. So this leads us to, as operators, lesser than 0. So this is a reason why we can produce the Riemannian matrix. And this is the procedure. And this is the whole spirit of what we have done there next week. But how does this relate with this diagrams, right? And the point is that I can show you how to construct these star diagrams. But I would like to present to you first a more complicated example that also appears in physical theories. That is what is called the de Sitter spacetime. And this comes from this star diagram construction in the same manner. So we have, forgot it here. Spacetime. So we have this SP2 that I just described to you. A, B, C, D, such belonging to S7 and S7, such that A, C, R equals to 0. And then we can take an SU3 here inside. We take SU2, sorry, inside SP2 to be nothing but this H0, 0, 0 here. So since we have quaternions, and by definition this belongs to S7 times S7, this is nothing but A down to the quaternions, such that A squared is 1. So inside SU2, we have a plane of S1s to shoot to make a vector. Yes, go ahead.
How this matrix A000 is S7 times S7 and S0?
Yeah, I'm just opposing a basic notation because here the columns here belongs to S7 times S7.
Yeah.
And each of these are quaternions. A, B, C, D are quaternions.
Yeah. Then 0, 0 cannot be S7.
Ah, yeah, of course, yes, sorry, yes, for sure. S7, and then we can push it here to be S3. Yeah, sorry. Yes, that's just opposing notation. Sorry. It's better now.
Well, if you want this to be a subgroup, maybe you put one of them.
One of the left, yeah, but now on the right side, yeah, we could do this, yeah. Sorry. put it here by the tree of it. Yeah, I don't need it to be as the rule, but that's great. Yeah, I just want to show you that I can take SU2 inside SU2, and then I can take S1 inside this SU2. It can repeat the action. So here I take M to be SU2, and I take G to be some S1 inside SU2, and we can repeat the procedure. So in the end, we're going to have this here, we have SU2 times S1, but S1 as a bullet, and going back to SU2, and then we have this S1, and then SU2, and choosing a Cheeger deformity metric, we can induce a family of semi-Riemannian metrics on this SU2. But the problem here is that they induce it SU1 action. What action can we take here on this SU2? We can take, for instance, this action here. We take, let's say, I theta belonging to S1 to act on this A0 by conjugation. We can take this, and this action has fixed points. So the points, so this action on SU2 has fixed points. So there are some points that do not have action vectors because the isotropy is everything. And since we do not have this, when you do this procedure to introduce Lorentz and matrix on the quotient by inductive deformations, there are some points where the time left existing. How can we interpret this? We can interpret this by looking to this diagram. Because here the action is free. And we have a semi-Riemannian submersion. And since here the action is free, we can see that these fixed points only exist because we are restricting the perspective of an observer to a lower dimensional space. So Cheeger deformations can be seen as a blowout from the point of view of blowing up singularities or fixed points. So here we have the time globally defined. But here not, because we are constraining the region of the observer. What if this is not a blowout? If you are not like raising dimension systems. So, and we have this semi-Riemannian here and here, but of course, SU2 has the universal covering SU2 times R, and we can take this Riemannian metric here to define a semi-Riemannian metric here. And this becomes a semi-Riemannian submersion. So this is nothing but the secure space-time. And the action constraint here by S1 has fixed point, but not here. So this metric is not globally defined as semi-Riemannian metric, since, well, there's points that the time slice exist. Well, but since this is just a dust in your eyes, because we have the view constrained by Latin dimension, we can indeed like continuate the metric along the fixed points throughout the time study. This can be done, and this is something that we have done. And this is more or less the whole story. And to finish it, we state some precise results, because we said just the thinking about the soft spheres is that we can do the same procedure using these cross diagrams to the global diagram, and then introduce equivalent global space-time structures on standard spheres and the soft spheres. And this procedure can be pulled back throughout the soft manifolds. So it seems that there is no distinction from the physical point of view of exoticity or not. But for non-compact spaces versus for R4, this is distinguished stuff. For the R4 case, the constructions can be made to distinguish aspects, but not in the compact case. So we would conjecture, for instance, that these manifolds would admit matrices of positive sectional curvature, since this is not true. There are some reasons why I think about it, and indeed, fixed points on analytic structures have everything to do with the existence of complex structures on the 6-dimensional sphere. But this is a totally different history. And just to state a final theorem here is that this is myself, Cavenaghi, Leonardo Cavenaghi, my PhD advisor said to me that since I'm young, whenever I go to a conference, I must take my full name. But I always think that it's more or less like too much ego, but I always say it's Cavenaghi, and then just put the C here. Yeah, so. And then we can see our theorem here is that whenever we have a cross diagonal like this, and prime, then we can build semi-Riemannian matrix here and here. And so that this stays when we have S1, because the actions here are just S1, bullet and star. This S1, they are isometric as metric spaces, and every in the G minus R4, G prime minus R4 are geodesically time and space complete. And they have reached what? So they are solution to some Einstein equations were supposed to be there. And this is the whole speed, since we can take, for instance, to be S7 into me, or sigma H S8, or the manifold with that was interested in dimension and not this years. And indeed, pretty much everything is not much. So I thank you very much for that.